Hello everyone. Once again, thank you for your flexibility in being a part of this online learning exercise. I hope everybody is doing well and staying safe and healthy. Last lecture, which was lecture 18, towards the end of the lecture, we looked at uniform distributed loading. So we're going to be continuing that today, and then we will be looking at a problem on frames. Okay. So the agenda for today is we will be looking at uniform distributed loading, and then we will be looking at frames. In this we will be solving a problem, and that's the best way to learn about frames. Alright, so we go to uniform distributed loading. Uniform distributed loading, as we looked at towards the end of lecture last time, this is the most general form of loading that can happen on a body. But then the loading is complicated, that we want to take something that is a uniformly distributed load and reduce it to a single equivalent force or a single resultant force. Okay, so I want to make a couple of key points about this one. Okay, so uniform distributed loading, the shorthand notation is UDL for us. So on a uniform distributed loading, an example of this is for example the wind hitting a signpost. Okay, so example is the wind hitting a signpost. And for example, if I actually draw such a signpost, right, let me try to do it here. So let's say that this is some kind of a pole, and here is a signpost. Okay, and let's say that this is fixed to the ground completely. Of course, it has to be supported, right? Because we're doing statics. We know all these things now. So let's say that the wind is hitting the signpost, and this would be the direction of the wind, or the wind force that is hitting the signpost. Okay, so this is an example. All of these are the wind loads, or a pressure load, as we looked at last time. Our idea is to take something like this, and then we want to reduce it. So we want to simplify it to the following situation, where we have the same signpost, along a fixed support, and rather than have the complicated forces that we see, we just want to have a single equivalent force, which we call as FR. FR is the resultant force, or a single equivalent force that has the same effect as the distributed loading. Okay, so FR in this case is the equivalent resultant force, and FR has the same effect on the body as the pressure load acting on it. Okay, so this is the big question is, how do I find FR, and how do I modify FR for different types of distributed loading? So the questions that we face are how to find this FR. Right, that's the first question, and this was something that we looked at last time as well. And the second question is, how to see where it acts. Okay, so where does this act? Where does this act? And both of these are aimed at simplifying the distributed load. Okay, so the aim of finding this FR, aim is to simplify the distributed load. Right, and this is an example of a distributed load in 3 dimensions. What we will typically do is we will take an equivalent slice in 2D, as we looked at last time, and then we will be analyzing it. And the most common types of distributed loading are the rectangular loading and triangular loading. Okay, so uniform distributed loading we will be looking at a two-dimensional situation. Okay, the common types are a rectangular loading, and there is a triangular loading, and you can also have for example, a trapezoidal loading, but a trapezoid is nothing but a combination of a rectangle and a triangle. So sometimes you can have a combination of these two types, which will be some kind of a trapezoidal loading. Okay, for our class, for MA 2010, we will be mostly focusing on the triangular and the rectangular type of loading, and so I'm going to take up a quick conceptual example of a rectangular loading, look at how to simplify this to an equivalent force, then a triangular loading, we'll simplify that to an equivalent force, we'll see where they act, and then we will get onto a problem in frames and machines. Okay, so we will look at the first example. So example 1, I'm going to be looking at the rectangular loading, and these figures are once again the figures that I typically take up are posted in your lecture figures on Carmen, and this is for lecture 19. So I'm going to be taking the rectangular loading and putting it on here. Okay, so this is an example of a rectangular loading, and you see here that you have what is called as the distribution, which is uniform, and the intensity of this distribution is called the load intensity. So let's say that if this is a distance starting from here is where I say that the x coordinate or the x-axis starts, then we know that the load here is x is equal to 0. So this location here is x is equal to 0. This location is x is equal to L. The intensity here is W at L. This is the intensity W at 0. This is the intensity W at some x, and you see that W at 0 is the same as W at L is the same as W at x. Okay, so for a rectangular loading, we see that rectangular uniform distributed loading, we see that the load intensity, which is W of x, is the same at all x, from x is equal to 0 to x is equal to L. Okay, so in this case, let me just say that this load intensity is equal to some, let's give it an example of 100 newtons per meter. Okay, which means that this is also going to be 100 newtons per meter. This is an example once again. This is 100 newtons per meter. Let's say that the length L is 2 meters, for example. Let's say that L is equal to 2 meters in this problem, and my aim is to get rid of this distributed loading and replace it by a single equivalent force. Okay, so let me specify our aim is I want to take this distributed loading. I want to put it here. Let's reduce the size of this guy. I want to take this and reduce it to the following situation. Okay, I want to take this and simplify it, and this is a simply supported beam. As you can see, it has a pin on one end and a roller on the other end. I want to simplify this to the following situation, so that I draw the beam, which is once again shown here, and then I have the pinned end here, and then I have the roller support here, and rather than have this distributed loading, and let's say that this is 100 newtons per meter, and then length L is equal to 2 meters, right? So this is a distance of 2 meters here for the length. Okay, and then instead of having the distributed loading, you see what I'm going to do is I'm going to draw it, but I'm going to draw it in a dotted line format, okay, and rather than have it this way, I want to replace this by means of this equivalent force, okay, or this resultant force FR. Okay, I'm going to be putting a dot there. So the idea is, what is FR and where does it act? Okay, and here is the key to solving this problem. Okay, so FR, first step is FR is equal to the area under the load curve, okay, or the load distribution curve, which is the same thing as the area under the load distribution curve. And that's fairly straightforward for us, right? Because if I take this figure from before, if I copy this and I put it here, okay, and I see that the load value is 100 newtons per meter. This is the load intensity W, okay, and L is equal to 2 meters, and this is the load curve. Okay, what is the area under this load curve? The area under this load curve is just a rectangle, so this is going to be the W, which is the height of the rectangle, multiplied by the width of the rectangle, which is equal to 2, which means that FR is actually equal to W times L for a rectangular loading. Right, this is nothing but the area, and in our case this is 100 so many newtons per meters multiplied by the length, which is 2 meters, which will give me 200 newtons. Okay, so this implies that for us FR is equal to 200 newtons. So we have already found out what the value of this equivalent force is, and the next step is, okay, I have this equivalent force, then I need to know where it is going to be acting, and that is the next key step. These are all actually things that can be proved if you look at your textbook on load distribution, uniform load distributions, and this is typically in a chapter where they do rigid bodies, 2D and 3D rigid bodies. You can see that they have actually proved these results. I'm just taking them as a matter of fact, okay, and I'm saying that FR has a line of action passing through the geometric center of the load curve. And this is fairly straightforward for a rectangle, because the geometric center of a rectangle is just at its center. Okay, so for a rectangular loading, the geometric center is at a distance of L by 2, or x is equal to L by 2 from either ends of the rectangle. And this way, now you see that I know where the force is going to be acting. It is going to be acting at a distance of x is equal to L by 2 or x is equal to 1 meter from either one of these ends, from either the x is equal to 0 end, the left side, or x is equal to 2 meters, which is the right side. Okay, so that if I now go back and redraw our figure from before, okay, so I'm going to take this figure from before, which I had drawn here. Okay, so I'm going to copy that. Excuse me. I'm going to be pasting that. I probably might have to cut out some of these pieces here. Okay, so I'll just cut off some of these extras. Guess it doesn't let me cut it out, but nevertheless, if I go back and copy this figure from before, pardon me for taking some extra time to do that. Technology is always a challenge, right? So I have the figure from before here. Okay, now we see that in this case we have simplified. So for us, after simplification, since we have the rectangular load, FR is 100 times 2, which is 200 newtons, and FR is at x is equal to L by 2, which is 1 meter from either ends. Okay, so this is the situation that is seen here, and so we can say that this distance here, starting from here all the way to where the force is acting, is L by 2, and likewise this distance here is also L by 2. Alright, so in summary, if you have a rectangular load, then the resultant force is nothing but the area under the load distribution curve, or the load curve, and this is the load curve as we have written it before. Okay, this is the load curve, and for us FR is essentially just going to be equal to 200 newtons, which is the height 100 times the length, which is 2. Okay, and it acts at a distance of L by 2 from either of these ends, which is 1 meter from either of these ends. Okay, so this is 1 meter, this is also 1 meter. Alright, this is the first example. This is a fairly silly example. All we wanted to do in this example was, okay, what is this value of FR, where does it act? Okay, then I take another example, which is an example of a triangular distributed loading. Okay, so this is the next example. Excuse me. It's a triangular distributed loading. It's slightly more complicated than the rectangular loading, but nevertheless still easy, because we know how to find the area of a triangle. That's not a big deal, right? So in a triangular distributed loading, as you can see here, for example, let's say that this is the start of our x-axis. Okay, so this is a horizontal axis that I set up, is the x-axis. This is x is equal to 0. This is x is equal to L, right? And let's say, for example, that L in this case, so say L is equal to 3 meters as an example. Okay, so L is equal to 3 meters in our example here. Then we see that this arrow that you see right here at the end is W at L. You see, this is W at 0, and this is W at some x, and you obviously see that because this is a rectangular loading, W at 0 is 0, W at x is drawn the following way, because it's some linearly increasing value, and W at L is the largest value. Okay, so in this case we see that W at x is equal to 0 is 0, and typically you'll be specified the value at W is equal to x is W at x is equal to L, or you'll be specified the intensity of the largest value. Okay, so typically we will be given the load intensity of the largest arrow on the triangular distributed loading. And one key point that I want to make, and I think I did not specify this when I did the rectangular loading, which also holds true for the triangular loading, is this point. Okay, I just want to make that point here. So the key point, the direction of FR is the same as the direction of the load intensity. That is, if the load intensity is pointing down, then FR is going to be pointing down. If the load intensity is pointing up, FR is going to be in a direction that is pointing up. Okay, so we come back to our figure, which is the triangular loading, and let us say that in our problem we are given the length is equal to 3 meters, and let's say that W at L is given to us as 200 newtons per meter. Okay, so say we are given L is equal to 3 meters and W at L is 200 newtons. We need to find FR and where does it act. Okay, these are the two things that we need to find out, and this is typically how I would look at the problem. Okay, so I bring the problem in again, and then I say, okay, this is the complicated situation that I have. In this problem I did not even draw the supports because this is just an example, but in the future we will have problems where there will be distributed loads and the corresponding supports acting. So let's say that L is equal to 3 meters, and I'm given the value of W at L is going to be equal to 200 newtons per meter. I'm sorry, so this has to be 200 newtons per meter. Apologies for that. I want to reduce it or simplify this to the following situation. Okay, so I have the beam here, and then I say, okay, this is the total length is given to me as 3 meters. That remains the same as before, so this is L is equal to 3 meters, and then I say, okay, previously I had this triangular loading, okay, but then my aim is to simplify that. So what I typically do is I draw the load, but I draw it in a dotted manner, and I say, okay, rather than do it this way, rather than have this complicated distribution, I want to replace it by a single resultant force. Okay, this force, as you can see, should be in the same direction as the load intensity. The load intensity is acting down, so FR is going to be acting down, and the question is, okay, what is the value of FR? The idea is fairly straightforward. Once again, we make use of the fact that FR is the area under the load curve. Okay, and this is the load curve for us, and this is a triangular loading, so which means for us in this case this is going to be half times W at L times the total length which is L. So in our case this is going to be half times 200, which is so many newtons per meter, times a distance of 3 meters, and which essentially gives us FR is equal to so 100 times 3 or 300 newtons. That is the first thing. The second thing is FR acts along the geometric center of the load curve. For a triangle, the geometric center is something that you have to remember. Okay, this is also something that we will look at when we hit the centroids portion of statics, which will be done towards the end of statics. But then FR, essentially in this case, FR has a line of action passing through the centroid of the triangle. in this particular case. Okay, and for a triangle, let me just specify the centroid location. We will look at this later. Okay, centroid or geometric center is the same thing. For a triangle is given by the following value. So if I have a triangle here, okay, I'm just going to draw one quickly, and let's say that this is the situation. If this is the length of the triangle is L, okay, length of the triangle being L, then the centroid location, which I'm going to be marking in the red color, is such that you want to essentially think of this as effectively, if I think of this triangle as filled with some amount of mass, where is the equivalent mass acting, and this is going to be leaning towards the heavier side of the triangle. So the centroid location is going to be at a distance of 2L/3 from the pointed end of the triangle. Okay, so that's going to be this distance here. Okay, so this is 2L/3, or a distance of L/3 from the other side. Excuse me. This is a distance of L/3. Okay, so the centroid of the geometric center of a triangle is at a distance of 2 times L/3 from the pointed end of the triangle. Okay, this is the pointed end of the triangle. Okay, and I just want to mark that here as well. So this is something that you want to remember. Okay, so please remember. This is not information that will be given in the exam and so on. And so in our situation, if that is the case, then for us, FR acts at a distance of x is equal to 2 times L/3, which is 2 times 3/3, or 2 meters from the pointed end of the load curve. Right, that's the second situation, or the second point. And the third point is the direction of FR. FR will have the same direction as W at X, or W at L, or W at L, it does not matter. And so for our problem, FR will be pointing down. Right. Alright, so if this is the situation, then we go back to our figure here, where we had these equivalent forces sitting, and then all I have to do is take all of these, and I want to copy them. Okay, and then I want to paste it here and say, okay, in our situation, what is the value of FR? So for us, FR ended up being half times 200 times 3, or 300 newtons, and FR is going to be acting at a distance, as you can see from here. Okay, FR is going to be acting at a distance of 2L/3 from the pointed end. So this is 2 times L/3, or 2 meters, and so this distance here is going to be 1 meter for FR. Okay, which is L by 3. Okay, so in this case you can call this point as the centroid, or the geometric center. This is the centroid. Okay, let me just rewrite that once again, just to be clear on my writing here. Okay, so this is called the centroid. I hope this is clearer than the previous time. Okay, so this acts at so FR acts at 2L by 3, which is 2 meters from the pointed end, and FR points vertically down. Okay, so these are the three things that you typically garner from this load distribution curve. And the basic idea is, okay, I have this complicated distribution, I want to simplify that, and this is the process of simplification. Okay, and this is something that we have to do for each and every problem that we encounter. And today we're going to be looking at a problem on frames where I have a distributed load acting, and then I want to see, okay, how can I first of all get rid of that distributed load, and then how do I find whatever I'm asked to find in that particular problem. Okay, so that's the end of uniform distributed loading. So we will now move on to frames. Okay, that's one a new concept that we will be looking at. Frames are typically similar to what trusses have been doing. You know, they are used for structural support. Okay, so frames are used for structural support. Okay, that is their main reason for existence, but there is a fundamental difference between a frame and a truss. Okay, so that I'm going to be writing as a key point. Okay, so key point, a fundamental difference between a frame and a truss is that, you see, when we looked at trusses, we always knew each and every bar of a truss to be a two-force member. That is not the case anymore. Is that each and every bar of a truss is a two-force member, whereas this is not true for a frame. It is not the case for a frame. It is not the case for a frame. It is not the case for a frame. Not the case for a frame. Okay, so this is a fundamental difference between a truss and a frame. Every member or every bar of a truss is a two-force member. It is not necessary that every bar of a frame be a two-force member, which means that you can actually have forces acting on the bars of the frame itself. So this implies that we can have external load acts on the bars of a frame. We know that in trusses, but in trusses the external loads act only at the pins. Act only at the pins or the joints. Okay, so this is the key difference between a truss and a frame, and you will see that frames are not any different in terms of handling their equilibrium compared to the rigid bodies that we've been seeing a few lectures back, when we looked at 2D rigid body equilibrium. All right. So best way is we will go into a problem. If you want to look at an example of a frame, then a bicycle frame is a good example. So I just want to make a quick note here. So for example, a bicycle frame, okay, where the frame is used for the structural support of the entire body, and of course you will see that there are forces acting at different portions of these members of the frame itself. Okay, let's go to a problem. I'm going to write up the problem here. Okay, and in this particular problem we will be analyzing each and every bar of the frame. Okay, so here is the problem. I have two bars. So here is one, and here is the other one. Okay, excuse me. Now these two bars are pinned to the ground. Okay, and here is the other bar. This is also pinned to the ground, and they are pinned together at the point B. Let's say that this is the point A, and this is the point C. And let me have some dimensions that are given to us. Okay, so starting from here all the way to there, and the distance from here to there, as well as from here to there. These are all given to us as the following. Okay, I'm just going to draw them as dotted lines. I'll have a nice 3, 4, 5 triangle set up for us. So this is 4 meters, this is 3 meters, this is 3 meters. Okay, so bars AB and BC are bars of a frame. Okay, so AB and BC are bars of a frame. Okay, the important thing is there is a force which is acting on the bar BC, and here is the force that is drawn. Okay, here is this force which is having a magnitude of 500 newtons, and it's acting at a distance of 2.5 meters from either pin B or pin C, and it's acting at an angle of 90 degrees. Okay, this is 2.5 meters. And you see that it's a 4, 5, 3 triangle, so the distance from where the force is acting to the point C is also 2.5 meters. Okay, so the force acting is a force of 500 Newton acts perpendicular to bar BC at 2.5 meters from B and also from C. Okay, so this is the situation, and the same problem could have been given in the form of a distributed loading. So for example, if the 500 Newton force were distributed loading, this would have been an equivalent situation. Okay, so I just want to draw an equivalent situation. If the 500 Newton force arose from distributed loading, okay, here is the equivalent situation that I want to draw. Okay, so once again I'll have the same bars BC and AB. Okay, so look at this. So in this case I would have this bar here, and then this is the bar BC. They would have been pinned to the ground as before, and there is a pin that is holding them together at the point B. This is the point A, this is the point C, and you know that the slope triangle is 3, 4, 5. So if I draw the slope triangle here, if I draw the slope triangle here, I can follow the same slope triangle for either of these pieces, right? This is going to be a 3, 4, 5 slope triangle, and likewise for this as well. Here I can say that this is a 3, 4, 5 slope triangle. Okay, so this is going to be 4, 3 and 5. Okay, so if I make use of that situation here, so this is a 3, 4, 5 slope triangle. Okay, so this is 3, this is 4, this is 5, and let's say that this distance is 5 meters from point B to point C, and it has the same angle as the bar AB with respect to the vertical. Now you see that the distributed load could have been in the following manner. Okay, I can say that we have a uniform rectangular distributed loading. Okay, and then you see that I can close this side here, and let's say that the load intensity is 100 newtons per meter. Now what you are seeing actually is that this 100 newtons per meter, and of course we will do this for other problems, as we solve more and more problems on frames and machines, we will see, take a distributed load, reduce it to a simple resultant force. This has been simplified into the equivalent force that you're seeing, and if I draw this situation as before, okay, I have the same bar AB and the bar BC. Not much of a change there. Okay, pardon the small differences in the angles, but they are the same angle. This is going to be A, this is the pin at B, and then this is at C. And rather than have this distributed loading, which I'm going to draw in a dotted line, okay, so I have this here, I have that there, and then I'm going to join them by this line here, and then I'm going to draw it as a dotted line. Okay, rather than have this distributed loading, I have this equivalent force now, which I'm going to be calling as FR, as you know. Okay, this is FR, and it's acting at the geometric center here, and for us FR is actually the area, which is 100 times a distance of 5 or 500 newtons. And this is the same as the force that you have been seeing given at the beginning of the problem, and you will see that since it is a 5 meter long distribution, this is going to be a distance of 2.5 meters, and this is going to be at an angle of 90 degrees. This is because the load intensity itself is acting at an angle of 90 degrees, as you can see from the distribution that is given on the bar BC. Okay. So this is simplified, and this is what is given to us in the problem statement, but in the future for different other problems we will be simplifying it ourselves. Okay, alright, so we go back to our problem, and I'm going to take this figure and I'm going to bring that down. Okay, so I'm going to copy that, and we come back to our problem. Okay, and here is the situation. Here is our problem. What are the things that we need to do? Okay, so obtain the reactions at pins A and C. Okay, pins A and C, and then obtain the force exerted by the bar AB on the pin at B. This is something new. And then obtain the force exerted by the bar BC on the pin at B. Okay, these are the three things to find from this problem, and we can see that this 500 Newton force, as specified earlier, could have come from a distributed loading. Okay, so I just want to point that out. This could have resulted from a distributed loading. See above. Okay. But the key thing here is there is a pin at the point A, there is a pin at the point C, and we need to find those pin reactions, and we need to find these new things, which are the forces exerted by the bar AB at the pin at B, and at the pin at and once again forces exerted by the bar BC on the pin at B. You immediately recognize that this is not a truss. This is because there is an actual external force acting on the body of the bar BC. Okay, so that's another key note that I want to make. So key, this is not a truss problem, because of the 500 Newton external force acting on the bar BC. Right? Such a situation would never have arose if we had a truss. We would not be having the force acting on the bar. We would actually have the force acting on the pin. It could be at either pin B or C or A. We don't know. We don't really care, because this is not a truss problem. But in any case, if this were a truss, this 500 Newton force would not be present on the body of the bar BC. Okay, so how to solve this problem? Okay, to solve this problem, to solve our problem, I'm going to break the frame into two pieces. Okay, so we're going to break the frame out into individual pieces. Okay, and what is the reason for that? The reason for that is the following. You see, I have a pin at the point A, I have a pin at the point C, which means that each of them are going to have two unknown reaction forces. But the total number of equations of equilibrium is only 3, which means that I cannot find all of these unknown reaction forces just by using equations of rigid body equilibrium for the entire frame. Okay, the reason, so I want to specify that reason. So the reason being, the reason for this, look at the supports. So support at A and C are pinned to the ground, which implies that I have a total of 4 unknowns. That is, I have AX, I have AY, I have CX, I have CY. Okay, but we will have we have only 3 equations for rigid body equilibrium. Okay, which implies that okay, hey, I cannot do this. I have to go ahead and I cannot look at the free body diagram of the entire frame. So this implies that cannot look at FBD of entire frame, as I cannot find all the unknowns from that. That is, cannot find all the unknowns, which is why we break the frame into its pieces or components. Okay, once again, just to reiterate what I was going to say, we cannot look at the free body diagram of the entire frame. This is because there is a pin at A, there is a pin at C, and there are two unknown reaction forces at A and two at C. So AX and AY, CX and CY, that's four unknowns. But I have only three equations of rigid body equilibrium, which means that, hey, I cannot do anything anymore, so I have to break this apart. Okay, so once I break it apart, here is what I get. Okay, so I go back to our problem. So back to our idea of breaking the frame apart into components. Okay, if I do that, I will be taking it on to the next page, and you see that if I break the frame into its pieces, I'm going to have the bar AB, I'm going to have the bar BC, and then I'm going to have the pin at B. Okay, of course I'll have the pin at A and C. I'm not too worried about those. So if I now draw the bar AB, so here is the bar AB, then I'm going to have the bar BC, which is going to be drawn here. Okay, and then there's going to be the pin at the point B, of course, the pin at the point B. And you also have the pins at the point A and C, but I'm not necessarily going to be drawing that because I know that the forces are pretty much the same at the pins A and C in terms of what they're going to be giving us, AX and AY and CX and CY. Okay, now here is the bar AB. Okay, so this is bar AB. So let's specify that. This is the bar BC. Okay, this is the pin at B. Okay, now we're going to be drawing all these forces. I start off by looking at the reaction forces. So I'm going to have a force AX and AY pointing vertically up this way, pointing this way. So this is AX, this is AY. Then I'm going to have a force on the pin at C. This is going to be CX. And I'm just taking them in some arbitrary direction. So these are actually the support reactions, right, at the point C and at the point A. Now here is what I'm going to be drawing, because there was actually a force acting on the bar. Once again, there is also a force acting on the bar BC. So I have this force which is of magnitude 500 newtons, making an angle of 90 degrees with respect to the bar BC, which is acting here. Let me take this and let's put this here. This is the bar BC, and likewise here is the bar AB, which is drawn here. Okay, and then here is the pin at the point B. Okay, so this is what we have so far. And I have some dimensions which I can make use of in our problem. Okay, so here are the dimensions. So I'm just going to be drawing those here and here as well, just to make sure that we have all these drawn up before we start solving the problem. So I'm going to be drawing that in dotted lines. Okay, so we know that this is going to be 3 meters, and this is going to be 4 meters, right, because we have the slope triangle of 3, 4 and 5. Now I'm going to have a set of forces that are acting at the point B. You see there is a pin at the point B. So on the bar AB, I'm going to be drawing them as the following. Watch this. Okay, so I'm going to be calling this as BX, and I'm going to be calling that as BY. Okay, and likewise on the bar BC, I'm going to be calling them by a different name. I'm going to be calling them as BX prime. Okay, and we will specify what they are. So this is BY prime, and then I'm going to be calling this as BX prime. And you see that because of the idea of action and reaction, at the pin B, I'm going to have equal and opposite forces BX, BY, and BX prime and BY prime. Okay, so on the pin at B, I'm going to be having a BX prime, I'm going to be having a by prime, which is going to be acting vertically down, equal and opposite. Please notice that this is a by prime, and likewise I'm going to be having a bx and a by, which is going to be equal and opposite to what I have on the bar AB at the point B. So this is going to be bx, and I'm going to have a force which is acting up here. This is going to be by. Okay, so there are several things that are going on. Let me take this figure and scoot it a little below what the situation is. Okay, likewise if I take this and show it a little apart. Okay, so here is the bar AB, here is the bar BC, and here is the pin at the point B. Okay, so this is the pin at the point B, and this is going to be bx prime as I have specified. Okay, and now you see that each and every one of these has to be in a state of static equilibrium, and we immediately start listing all the forces. Okay, so let me list all the forces which are acting on the bar AB, the bar BC, and the bar pin at B. Okay, so let us list all the forces. Okay, so on the bar AB, you will see that the forces are the support reactions, at A, which is AX and AY. Then you will see that there are forces at the point B which are BX and BY, and the key thing is this: these forces BX and BY on the bar AB are the forces exerted by the pin at B on the bar AB. Okay, these are the forces exerted by the pin at B on bar AB. Okay, then I go to the next bar. Okay, so on bar BC, okay, what are the forces? I have support reactions at C. As you can see, I have support reactions at C, which we will call as CX and CY. Then I'm going to have once again the external force of 500 newtons on the bar BC. Importantly, third thing is I'm going to have a force Bx prime, By prime. I just called it by a different name because at the beginning of the problem I do not know if they are the same as Bx and By. Okay, so I just want to make a quick note here. Okay, so note, I called it as Bx prime and By prime because we are not sure if Bx prime is the same as Bx and if By prime is the same as By when we start the problem. Okay, but then hopefully so this is the note that I want to keep in mind here. Okay, but then we hopefully realize that okay, they're all probably going to be the same at some point, and let the equilibrium equations dictate that they're going to be the same. Okay, so in this case if I write out the list of forces on the bar BC, I have the forces at B, which is Bx prime and By prime. Okay, these are the primes on Bx and By. Please notice that. Okay, these are the forces exerted by the pin at B on bar BC. Okay, these Bx prime and By prime. And once again, I just want to point out that we call them as Bx prime and By prime because we are not sure if Bx is the same as Bx prime and if By is the same as By prime when we start the problem. But if we eventually find out that they are the same, then well and good. Okay, so these are the forces. Then on the pin at B, I have two sets of forces, Bx and By. This is the force exerted by the pin, by the bar AB on pin B, and the second set is Bx prime, By prime is the force exerted by the bar BC on pin B. Okay, so this is the situation that we are ending up with so far. Okay, and the idea that we are going to be making use of is that each and every one of these are in equilibrium. Okay, so the basic idea is that each part is in static equilibrium. Okay, which implies that I can take the pin at B and then analyze it by using equations of static equilibrium, which means that take the pin at B, so take pin B and apply static equilibrium. Okay, and so if I go back to pin B, okay, so I'm going to take pin B and I'm going to copy that and bring that down here. If I now do that, okay, I see that sum of all the forces in the x direction is equal to 0 because this is the particle or a pin, right? We don't have any moment balance equation, so we say, okay, sum of all the forces in the x direction is equal to 0. This implies that Bx is equal to Bx prime. If I sum all the forces in the y direction and set that equal to 0, I get By is equal to By prime. Okay, this is an important thing that we have obtained here, and the moral of the story is the following. If there are only two bars connected at a pin, okay, so for example, in this case I have the bar AB and the bar BC connected together at a single pin, then the forces on these two bars due to that pin are equal and opposite. You see, Bx is opposite to Bx prime, By is opposite to By prime. So I want to make that note before we conclude today's lecture, and I'm sorry I went a little over time. We will be coming back to this problem, and we will be starting off with this problem in the next lecture and then solving it. And so the key summary is that if only two bars of a frame are connected at a pin, so for example bars AB and BC at pin B, example, and if no other external or reaction force acts at pin, okay, that's not necessarily at pin B, at that pin, then the forces of the pin at the two bars will be equal and opposite at the pin location. And for example, as in our case above, bx is equal to bx prime, by is equal to by prime. And the idea is, if this is not the case, then what do? Is we have to analyze the pin as a separate rigid body and then apply equations of rigid body equilibrium. So from the next time onwards, if there are only two bars connected at a pin for a frame, and if there are no other forces acting on the pin, then the force of the pin on those two bars is going to be equal and opposite. So we will make use of this directly. So this will be used directly, and if we encounter a situation of this sort, if we encounter such a situation, then we do not need to draw the free body diagram of the pin. Okay, so this is the summary that I wanted to have for this particular problem. Okay, and in the next lecture, I just want to make a quick note. Okay, we will come back to this problem. Okay, to this problem and solve it for the unknowns, which is ax, ay, cx, cy, and bx, which is the same as bx prime, by, which is the same as by prime. Alright, thank you very much, and once again apologies for slightly going a little above our time, but I hope that this is going to be useful to all of you. Please take care of yourselves, and I will see you all from an online perspective in lecture 20. Thank you.